Hey AP Physics students. Today I am going to be talking about forces, along with the force equations, free body diagrams, how motion comes into play, and then specific types of forces, friction, and Hooke's law. So make sure you have your equation sheet out and let's get ready. A force in physics is generally described as a push or a pull. And I think this really makes this unit challenging because it's such a generalized concept. When we talk about types of forces, we have about 7 that we talk about in physics. First, we have gravity, which is in every single situation. If we remember from last unit talking about motion, this is always downward. So this is when we get into the force of gravity versus gravity, okay, and how we use both of those. And I'll talk a little bit more about that when I look at free body diagrams. Applied force is really any push or pull that we have. So you could be pushing something across a floor, you could be pulling something up a ramp. Our third type of force, and sometimes probably the most confusing, is our normal force. Our normal force is only when an object is on something else. So for example, if I have this box that is sitting on the ground, I have my force of gravity, but I have to have something balancing it out. So that's where I have my force normal or support force. It's really important to note that this is always perpendicular to the surface. So if we're in a ramp and I have a box on this ramp, my gravity is still straight down, but my normal force is perpendicular to the surface. We're not getting into this in this part of the unit, but I just want to note the perpendicular nature of normal force. Then we have friction and spring force, which we'll be getting into later in this lesson. And then we also have tension, which we will be using when we think about things that are hanging. Finally, we have air resistance. You'll notice on the back of your equation sheet, this is not typically used in the AP Physics world here, and it is something you should not be including in any of your free body diagrams except if it is specifically noted, and you can see this note on the first page of your equation sheet at the bottom. I just mentioned free body diagrams, and free body diagrams in physics are one of the essential ways that we show understanding in really any concept with forces. A free body diagram is really just a sketch of the object, so a box or a circle, and then I'm showing all the forces that are acting on that object. You'll notice when I wrote this free body diagram here that my arrows went out of the object. So this is an example of a ball dropping. We have force of gravity acting on it and nothing else. Now, what is our technique to do these? Well, we're given a situation, and if I need to draw them, what I like to do is go through each of those 6 to 7 big forces to see what is acting upon it. So let's say that I have a box that is being pushed to the right. Okay. I have my force of gravity, and then I have my support force. Now we know because this object is only moving in the x direction to the right that these are equal. So I'm going to use these tick marks like you do in math class to show that these things are equal. Now to show that this is being pushed to the right, I would also have an arrow, and I could just say force applied here. Now maybe I have friction the opposite direction, and I'll get to that later if I had force of friction. And I would also note that these are not equal. I think free body diagrams are really something that is all about practice. So looking at different situations and being able to draw that out. Let's move on to some of the equations that we're going to use. Really, all of forces boil down to this equation, which is Newton's second law. Typically, you see this as force equals mass times acceleration. However, in AP Physics, we solve for A. Now, what really is the difference between motion and forces? Well, it's that mass is actually coming into play now. Now, when I rearrange this, acceleration is still the same in meters per second squared. This sigma, always in science, is net or total. My force here, the units we're going to use are newtons, and I will tell you a little bit about those later and what they actually are. And then mass, we use kilograms in physics. You'll see in the last part of this, they just wrote force net instead of using sigma. Let's talk a little bit about the units, and I like to figure out the units by looking at our rearranged equation. For mass, we use kilograms, and for acceleration, we use meters per second squared. That means if you forget newtons, you can just use this. This combination, kilogram meters over second squared, is what we just use for N for newtons. So it's one of our first variables. This is one of our first units that are an abbreviation. But like I said, you can always write it out as kilogram meters over second squared. We're going to use this equation to talk about net force or total force, and I'm going to use it rearranged for net force. This entire unit boils down to this equation and then within that two situations. And that's when my net force is 0 and when my net force is not 0. Now, my first situation, everything has a mass, but my acceleration is 0. We know from motion that these are only two situations, when something is at rest and when something is at a constant velocity. That is telling us that my net or total force is 0. Then we have the other side, and we have my net force is non-zero. We always have a mass, but my acceleration is equal to some number. What the big part about this is every single situation we go into, you have to think, is my net force 0 or is my net force non-zero? And as we get into this unit, we're going to explain a lot, but this diagram right here is really going to help you as we look at some different situations along the way. One of the first things that we're going to focus on is motion plus forces, and we're going to tie those two together. We are going to do some derivations and start focusing on using variables instead of using numbers. This is saying a ball with mass m slows down from an initial velocity v to a stop, and it covers a distance of 2d. It says, what is the force needed to stop the ball? In this situation, I don't have to make a free body diagram. Instead, we're just going to solve for this force. I know eventually I'm going to need to use F equals ma. I already know m, but I'm going to have to solve for acceleration. Now let's write down our variables here so we kind of get a grasp of what's going on. So my mass, we're using m. I know that my velocity initial is v, and my velocity final is 0, and my distance is 2d. And we first need to solve for acceleration. Once again, I know my mass. I don't know what acceleration is. Right now, we need to take a moment, look at our equation sheet, which one would work. If you guessed the third one, you are correct. Now, in these situations, I still want to write out my entire equation, and then I'll take a minute to solve for the variable that I need. Now, after this is when I plug in my variables, and I'm plugging these in instead of numbers. Okay, think of them like numbers. So 0 squared minus v squared over 2 times 2d. Let's make this look nice. Negative v squared over 4d. Okay. Now what's cool about this is once I get this generic equation, I could just plug something in if given for velocity initial or delta x. Now I know that I need to figure out what is my force, so I can just plug this in to this equation right here. And that will give me my answer. AP style loves this. No numbers, just plugging in variables to get an answer. All right, let's look at some more specific types of forces that we're going to see. Let's talk a little bit about friction. Friction in real everyday situations is always happening. When I look at friction, if we look at this free body diagram, we'll see that we have something that's being pushed across the ground. We have force applied, force normal, and force gravity equal to each other, and then this force of friction. Force of friction is an interesting force because it is dependent on the weight of the object and the material that it's being pushed across. Now let's look at the equation. My force of friction is here, so we typically write it with the small f. And then we have this value here, which is mu. Don't call it that. Call it its real name, which is the coefficient of friction. We'll talk about what the heck this thing is soon. And finally, we have our force normal, which is our support force. Sometimes we say that this is the weight of the object, but not always. And that's something I really get into class to clear up the difference between force normal and our weight. Let's go back to this coefficient of friction and what this is. Now, you'll notice that we have this less than or equal to. Okay, when we write this, a lot of time we'll just write it like this, but this is telling you something very important. And that is the force of friction is always less than the force normal, all right, which is going to be very important to us as you go through some of your work. Typically, we just write it like I did down here. Now, if I rearrange to solve for my coefficient of friction, I'll get force of friction over force normal. Now, if I look at my units, that's newtons over newtons, which equals just 1. So my coefficient of friction is a unitless variable. Kind of interesting. We're going to see a couple of these. All right, so it's really just a proportion here. I'm just introing this. This is something that we will get into. How do we use force normal? What exactly does this mean a little bit later? This is really something that we apply to a lot of different situations. Let's talk about our final equation here, which is Hooke's law. You'll find this at the bottom of your equation sheet in the left column. Hooke's law is our spring force. Okay, so we have a spring. Typically it's going down. And what will happen is I'll put a mass on it. When I put that mass on, we'll see that this thing expands. And what we have to figure out is, what is this K value? And my K value is my spring constant. And it is similar to the coefficient of friction because it is a proportion. You'll see that we have this X here, and this is the amount of stretch that happens. So it's not the actual length of the spring, but the difference for the stretch. Now, Hooke's law, once again, is typically written like this. I personally like to write delta X as a reminder that it's the change, okay? This K is the spring constant, and if I rearrange, I have force spring over delta X. So for my units, I have newtons over meters. In this flipped lesson, I didn't do a ton of examples. I really just went over the basics of forces. Now, this means that during class, we're really going to apply these to a lot of different situations. This is truly a unit where there are almost endless possibilities of what we're going to see this applied to.